Okay, now we have a follow-up question to that Bernoulli's tube question we just did. We have again 2.5 atmospheres, we have radius 4, and let's say that as the tube is going up, there's a column of water here, sort of midway, and then there's some water resting here. I want to know what the height of that column of water is above the tube, okay? So what's given here is that as it's narrowing, at some point around here, the radius of the tube becomes 2 meters. So it goes from 4 meters to 2 meters. And then the center of the column of the tube, from here to here, it rises by 3 meters, okay? This picture should be a little bit better drawn, something like this. So it can make a little bit more sense. So it should be the tube is narrowing like that. Okay, so between here, this one will be from here to here, then it's going to narrow a little bit more. Okay, eventually until it becomes, the radius becomes 1 meter, right? So between here to here is 2 meters, and then from here to where the center of mass was, that one is 3 meters. So the center of the tube has gone up by 3 meters. So how would we approach that? How would we find the height of the column of water? And then here it's open to the atmosphere, okay? So this one, we're going to use that same equation, but we're going to solve for what the pressure of the water here is as it's flowing up. So we're going to have P1 plus rho g H1 squared V1 equals pi times 2 squared. Here the radius is 2. Times V2, pi cancels, 16 V1 is 4 V2, V2 equals 4 V1, okay? So the velocity here of the liquid is going to be 4 times the velocity of this, so it's not like this one which was 16 times as much. So with that we found the relationship. We know this one is 2.5 atmospheres, okay? And then this one we're going to set it equal to 0. Plus half rho V1 squared is equal to P2 plus rho GH2 plus half rho, and then V2 we're going to put 4 V1, and then we're going to square that. So we have here 2.5, okay? And remember, an atmosphere was 1.013 times 10 to the 5 plus half. We're going to have here 1,000 V1 squared. P2, we're going to solve for it. This one is 1,000 times 9.8. And then H2 was 3 meters. Plus 4 squared will be 16. 16 divided by 2 times 1,000 times V1 squared. Okay? So 0.013 times 10 to the 5 plus 500 V1 squared, and then this one is going to come onto the left side. It's going to be minus 2. So essentially we're solving for what the pressure of the fluid here over here in while the radius is 2 meters and the tube has gone up 3 meters, right? So we need our knowledge of the V1, which we found from the first example, right? V1 was 0.65. V1 0.65 meters per second. So we take our knowledge of the V1 as we found from the first example and apply that to the V1 in this example. So we have here 2.5, 1.013 times 10 to the 5th. 500 minus 8,000 is going to be negative 7,500, right? You can combine them, 8,000 minus 500, 7,500, V1 squared. So 0.65 squared, okay? That's going to give you this one minus this one, and then you're squaring the V, minus 3,000 times 9.8. That gives you pressure P2, okay? So let's put all that together. This is pascals. If we wanted to know how many atmospheres that was, we would divide that by 1.013 and divide it by 10 to the 5. So we would convert that to atmospheres, it would be 2.178 atmospheres. You see, remember, the atmospheres is 2.5. By the time it goes up, the atmospheres has got to go down to 1 atmosphere. So it's going down gradually, okay? So over here is 2.178 atmosphere. Eventually it'll go like 1.5 atmospheres, and it will finally end up at 1 atmosphere. So what will be the column of the sitting liquid of water, okay? The more the pressure here is, the more the sitting liquid of water will go up, right? If the tube is short, let's say the tube is over here, the water might go and completely spill out, okay? And it will spill all on the ground over here. So depending on how long the tube is, the water might just go up and completely just spill, okay? So how do we find that? Well, the pressure here and the pressure there are related, okay? So we're gonna say the pressure atmosphere, okay, plus the density of water GH, that's equal to the pressure of the fluid over here, and that's just equal to our, what we're calling our P2, right? So that would be 220,000 681.25, and that's equal to the pressure of the atmosphere, okay, which is equal to 1.013 times 10 to the 5th plus 1,000 here. This one's going to be 9.8, okay, times H. So we take our answer, 220,000, we subtract 1.013 times 10 to the power 5, okay, so we get that. Then we divide that by 1,000 and 9.8. So divide by 1,000 divided by 9.8. Okay? So we get the height of the column of water, 12.18 meters. So it's good to have a column of water like about 15 meters, that way you're safe, 20 meters or something, okay? So 12 meters will not spill. Okay, so this is a good example of building on the previous example and then applying it to also the pressure variation in a fluid which is open to the atmosphere. Okay, so we used our previous example's velocity to find for the pressure in the fluid at a certain point in the tube, and then we apply it back to the column of water. Okay, so hope this helps and gives you another example of the usefulness of Bernoulli's equation. Thank you very much.